Okay, so we're going to trace through another situation of linear search where we're looking for a number that's actually not in the list. So we're going to reuse the same pseudocode, but now we're going to trace through the linear search algorithm to look for the number 3, which we can see is not in this list. Essentially what we're going to have to do is go through every item in the list until eventually we find that it's not in the list. Now, this will take a little bit of writing. I'd probably give you a shorter list to look through if you had to trace through this on pen and paper, but just for the exercise and the extra repetition here, we'll do this one as it stands. So again, we start with I equals 1. We can label these A1, A2, A3, A4, A5, A6, A7, A8, A9 for future reference. That means that the n equals 9 again. It's the same list as the previous example, but if you hadn't watched that one, this is fine. Now the first question we ask ourselves is 1 less than or equal to 9. That's true. And then we ask ourselves, is 3 not equal to 4, which is what's in A sub 1, and that's also true. So we move to the next one. 2 less than or equal to 9. 3 not equal to 7, also true. So we move increment I up to 3. 3 less than or equal to 9. You can hopefully see what's happening here. We have to compare I to 9 every time, and then we have to compare the number 3, the x that we're looking for, to each item in the list. Okay, so we will continue to do this, but only a few more left. But again, I would try to keep this smaller if we had you doing this in a timed environment. Okay. I is 6. 6 is less than or equal to 9. 3 is not equal to A sub 6. I skipped one here, so I actually made a mistake. This here, previous one, I skipped the number 9. Okay, we're not equal to 11. I becomes 7. 7 less than or equal to 9. 3 is not equal to 12. I becomes 8. 8 is less than or equal to 9. But 3 is not equal to 8, which actually A sub 8 is 8. Right, but it's the A sub I we're looking at now. I equals 9. 9 is in fact less than or equal to 9. Right, that's fine. 3 is not equal to 5. That's true. So now I becomes 10. Okay, and then we say 10 less than or equal to 9. That becomes false. Okay. Remember that the while statement will exit as soon as one of these conditions becomes false. In the first example, we were looking for an item that was in the list, so we exited when we found it, when the x was no longer not equal to A sub I. In this case, since the item's not on the list, we're going to exit when this first condition, I less than or equal to n, becomes false. 10 is no longer less than 9, so now when we do our comparison at the end, is 10 less than or equal to 9, the answer will be no. Right? So the last condition would be 10 less than or equal to 9. The answer is no. So instead of location getting the number 10, location will get the number 0, and that will be an indication to the user that the number was not in the list. So we have to go all the way through the list looking at each number one at a time until we either find it or run out of things to look for. Once we get to position 10, we're beyond the end of the list, and then we return the number 0 to indicate that we didn't find it. Okay, it's certainly easy for us as people to decide whether or not the algorithm is in a list, but the tracing of the algorithm on paper is what we're really being asked to do here. How would a computer do it? The computer doesn't have the ability to process the whole list at once. It can only look at one entry at a time. So on a quiz or a test, you'd be asked to trace through this algorithm, and you'd have to show a record of all the comparisons that you did along the way. Now it's time for you to go practice some, and then we'll move on.